So we ended the last video by noting that what you might call Bayesian confirmation theory, or Bayesianism about scientific theory confirmation, suggests that this is how theory confirmation works. You identify the prior probability of a theory, you identify the probability of some observation, and you identify the probability of that observation given some theory, and you use that to assign a probability to the theory given that observation. So this is how you update belief. When you make a new observation and you want to change the probability you assign to a theory given that observation, you put these things together and you treat this as if it's just a function of those, as if it's determined by those three. And now what I'll do is I'll give you an example in which this works out really neatly and cleanly, and it's pretty clear that it seems reasonable to restrict yourself to just these three things, and it seems pretty clear how you identify these three things and how it's clear that they give you this. And then we'll look at an example where it's less clear. So this is an example of a kind we've looked at before towards the beginning of the semester. So we test a group of Olympians for steroids. The test produces 80% positive results for people who use and 70% negative results for people who don't. To put it another way, the test is 80% accurate for users and 70% accurate for non-users. And we know that 10% of the population at issue are users. Now we have a randomly selected individual who tests positive. What is the probability that he or she is a user? Well, the prevalence in the population is 10%, and we can think of that as the prior probability of the hypothesis. That is the probability of the theory independent of the observation. So what we've been calling here PT. The test is 80% accurate for positive results. That's how strongly the theory that someone is a user predicts the observation that they test positive. So that's this, the probability of the observation given the theory. It's 70% accurate for negative results. And you can sort of put this together to generate the probability of the observation, which you'll see now. So assume there's a population of 1,000 people. How many use? Well, 100, because 10% of the people use. So that means 900 don't. For those 100 users, how many test positive? Well, there's going to be 80 positive tests because the test is 80% accurate for users, so it's going to get catch 80 of the 100. For the 900 who don't use, how often is it going to give a positive result anyway? Well, 30% of the time, because it gets things right 70%, so it gets things wrong 30% for this group. So you're going to get 270 positive tests from non-users because 270 is 30% of 900. Then how many total positive tests? Well, you get 80 from people who are users, 270 from people who aren't. So there's 350 total positive tests. So as we saw before, the odds that you're a user if you test positive are 80 out of 350. That is, out of every 350 positive tests, 80 come from people who are actually users. I said before, this is the prior probability of the theory. So we can treat the theory like as if it's X uses steroids. The person who tested positive uses steroids. The observation is the positive test. The prior probability of the theory is 10%. That's how probable it was that that person was a user, independent of the observation that they tested positive. The probability of the observation given the theory is the accuracy of the test, how strongly the theory that their user predicts the observation that they test positive, and that's 80%. And then what's the probability of the observation? Well, you're going to get 350 positive tests out of 1,000 because you get 80 from people who use, 270 from people who don't. So 35% of the time you get a positive test, 350 out of 1,000. So 35% is the probability that you get the observation of a positive test. So putting that together, you get 23%. Your 80% times your 10% divided by your 35%, your probability of your observation given your theory, times the probability of theory divided by the probability of the observation. And in this case, 23% is the correct answer, given these starting points. So it all looks clean and beautiful. And it looks like this way to confirm, this way to assign a probability to a theory given an observation is a great way to do it. Now let's look at the Messier case. So here's the Messier case. Let the theory be that carbon emissions cause increased energy in the atmosphere, which in turn causes climate disruption. The question is, how do we assign a starting point? How do you assign that prior probability for this theory? It's not like, in the previous case we said, look, we assign the prior probability for X uses steroids by looking at the percent of people in the population who use steroids, and that was 10%, so we just made the prior 10%. But here we can't look at the frequency with which this theory is true across all possible cases because there's only one case. So here we can imagine that you have two people, they're going to assign the priors in very different ways. Like maybe this person says, before considering any evidence about whether climate is, temperature is going up or down and there's more energy in the atmosphere more generally or decreasing energy or constant energy, I think it's very unlikely that carbon emissions are affecting the atmosphere in any interesting way. Maybe because I think it's very unlikely that anything we do could have that profound effect on the environment. And over here you have Van who says, look, I don't really know anything about this issue either way, so I'm going to start at 50%, perfectly neutral. Now you might think a prior of 50% seems like a weird way to be neutral, but let's just say that's okay. Now we get this observation that the average temperature of the Earth is increasing, storm intensity is increasing, ocean temperature and value is increasing, and so on. More generally, there's increased energy in the atmosphere. Now, how are each of these people going to react? Well, you could imagine that Fred says, look, the probability that you would get this observation, that energy in the atmosphere is increasing, given the theory that carbon emissions cause that, since carbon emissions have been going up, it's very high, 99%. You can imagine that Van agrees. Now the observation is the same in each case, so let's just say they each say there's a 50% chance of getting that observation. I don't know where I'm getting that from, but that's part of the point, is like, how do you figure out how probable that observation is? Who knows? So what I want you to see now is just this. Because they had different priors, 1% versus 50%, they end up with very different posteriors, very different conclusions, posterior probabilities they assign after taking that observation into account. Fred says 2% probability this theory is true, so it's most likely false. Van says 99% it's true, so it's most likely true. So radical disagreement because of different starting points. And whereas in the case where we had a prevalence of 10% in the population, and we use that to set our prior, it's just unclear how to set the prior here. But the prior has a profound effect on the posterior, on the probability you should end up assigning to the theory given that observation. So the point is, even on this like neat, clean kind of mathematical Bayesian framework, actual scientific theory choice is going to be very messy. Now, this isn't to say that there aren't ways to try and set the prior. Like one way people think of maybe setting the prior is your scientist uses their intuitive judgment, where their intuitive judgment is going to be based on how often similar theories have been true in the past. And Fred might say, theories of this kind have been true in the past, only 1% of the time, and Van says 50% of the time. That's maybe one way you can do it. So the point isn't that there isn't a way to sort of fill this out. The point is just that it's trickier than the simple kind of clean case like the steroid